Hi guys, welcome to Mindset Learn Extra, and we're doing physical sciences. This is the grade 11 show. Please don't panic, we're in good hands. We've got Bruce with us this evening, and I'm here to make sure that I take all your questions from Facebook, so please get in touch with us, post on the page, and we'd love to hear from you. Remember, we're also on Twitter, is at Learn Extra, and we'll be chatting with you and taking your questions. Bruce, what are we doing today?
John, thanks very much. Guys, yes, what we're having a look at is a continuation from electrostatics from last week. So everyone who had tuned in last week, guys, grab your books. We're going to be doing a continuation of this, and we're going to be concentrating mainly on electric fields today. So that's what we're going to be doing.
Great stuff. Field theory. There we go. Very good stuff. Excellent. Remember, that's not picking up the daisies, but it's about charges. So let's get into it, and we're going to go to a short break, and then Bruce will take it away. Welcome back, grade 11s. This is a Learn Extra, and we've got a great program lined up for you. We're going to be dealing with electric fields. It's all part of electrostatics, and we're going to make sure that you stay in tune because we've got some great prizes to give away. There's a Casio calculator. I'll tell you a little bit about that later in the show. We're also going to be showing you a clip towards the end of the show of Meeting the Mindsetters, so stay tuned to that. It's a campaign that's been going on Facebook, so make sure you don't leave your seat. You're going to meet the mindsetter from last year. He stayed with us, he worked with us through the year, and he got 100% for physical science. Can you believe it? That is going to be a great little insert that's coming up very soon. So let's get straight away. I'm taking it over to Bruce, and we're getting into electric fields.
Great, John, thanks very much indeed. And I must admit, I'm looking forward to a little insert as well, to see a mindsetter who actually got 100% for physical science. That's a great achievement. And no doubt he was there watching the shows, making sure that he learned as much as he could from the shows that we delivered for you guys. But guys, what we're going to be looking at today is going to be electric fields around charges. Now, you remember last week we spoke about Coulomb's law, and I just want to go back and do a quick revision about Coulomb's law for you guys, just so that we understand the concept of Coulomb's law, because that takes us really nicely into the concept of electric fields, and then we can move through with today's lesson. So I'm just going to pull up a blank page up onto the screen, and we're going to have a look quickly at our Coulomb's law. So let me select a nice color for you guys, and I think this was always a nice one that worked, and we're going to have a look at Coulomb's law. Okay, now guys, you'll remember Coulomb's law dealt with the forces that existed between charges. So if I had two charges, and let's make, I'm just going to call them Q1 and I'm going to call them Q2, okay, and let's say the one was a positive charge and the other one was a negative charge, straight away all of you guys should be saying, well, those two charges are going to attract each other. Absolutely, because we know that unlike charges are always going to attract. And if I had, for example, let's just bring this down a bit. If I had a plus Q over here, I'll call that Q1, and let's say we had plus Q2 over there, then we've got like charges, both positives, and we're going to get repulsion. So what we've got over here is basically attraction over there, when we've got our unlike charges, and when we've got like charges, we're going to have repulsion. Okay, and we also stated that the magnitude of that attraction or repulsion is going to be directly proportional to the magnitude of the product of the two charges, and then it's also going to be inversely proportional to the square of the distance between their centers. So if I had to draw in a distance there, a distance of separation, which we call R, and I'm going to draw it in both examples like this. There's my distance of separation like that. What we were able to do, and I'll just extend the page slightly, we were able to set up our Coulomb's law equation, where F is equal to K Q1 Q2 over R squared. So in other words, guys, we've got the product of the two charges, okay, either like charges or unlike charges, it doesn't matter. We've got the square of the distance between them, and then we had our universal constant, our Coulomb's constant, or electrostatic constant, of 9 times 10 to the 9 newtons per square meter per coulomb per coulomb. And that, guys, you'll remember last week is where we ended up, and we were able to work out and calculate the magnitude of this force of either attraction or repulsion. Okay. Now, what we're going to be having a look at today is to go in a little bit deeper into the subject and ask ourselves the question as to how these objects are going to, or these charges are going to attract each other, how they're going to repel each other. And that's all got to do with the electric field that is generated around those particular charged objects. Okay, so from here, let's hop now right into the lesson, and we'll bring it up and bring up our first slide. And as I've said there, we have got our heading electric fields around charges, and the important thing to remember, let's bring this down, scroll this a little bit, is that all charges have an electric field that surrounds them. That's the important thing. The charges have an electric field that surround them. This electric field is responsible for the charge experiencing a force of attraction or repulsion. Just what I've said now. Okay, so guys, we can define now what an electric field actually is. And here's a very important definition for you. The electric field is measured as the force that a positive test charge would experience in that field. A force that a positive test charge would experience in that field. Okay, now that's a definition. We're going to make that definition more understandable as we work through today's lesson. Okay, guys, so just take note of it, and then we'll examine it and we'll flesh it out a little bit more for you. Okay, but while we do that, I want us to have a look at how we represent this electric field. Okay, so electric fields surround the charge in all directions, and that's what I said right in the beginning. It's very important to note that your electric field is going to be 360 degrees around that charge. And we call this a radial field. Okay, a radial field means it's now it's being exerted, or should I say being formed, in all directions. So if this is now my charge, this over here is my test charge, which I'm going to call my positive test charge, which I'm going to call Q, and this is the charge that is going to experience the force in that particular electric field. Now guys, please have a look now at the electric field pattern that I've got there. I've got a positive charge, okay? And I know it's a positive charge by looking at the direction of the electric field lines. If it's radial, we must show the field lines moving in all directions, 360 degrees around that charge. And notice, guys, that the electric field lines are moving away from the charge. In other words, very important to notice that the field lines move away from the charge. Okay, now, if I now bring up a negative charge, okay, a negative electric field pattern, guys, very similar in that it is radial, and yes, there's my test charge, and my test charge will also experience a force. However, notice, guys, that the electric field lines are now pointing towards the actual charge that's creating the field. Okay, so guys, important to note, quick recap, let's go back up slightly. Positive, notice the lines are moving away from the charge, okay, and the negative field, the lines are moving towards the actual charge itself. Very important that we get our direction of these field lines correct. Okay, right, sorry, scroll down a little bit more. Okay, we've spoken about the concept of radial fields, okay, in other words, 360 degrees around those particular charges. And then what I've got here are just a couple of very simple rules that you must follow if you're asked to draw an electric field pattern, either around a positive charge or around a negative charge. Now, you're never going to get tested these rules. In other words, they're not going to say in a test or an exam, write down the 3 rules of drawing electric fields. But they're going to ask you to draw electric fields, and you must apply these rules in drawing these fields themselves. Okay, so first of all, what's the first rule? Well, there's an electric field at every point in space surrounding a charge. And that we know from our concept of radial fields. Okay, at 360 degrees in 3-dimensional space, there's always going to be an electric field at every single point. Okay? The second thing there is that field lines are merely a representation of the electric field. Okay? They're not actually real. All right. So in other words, when I hold a charged object, there aren't actually lines drawn coming out from them. They just represent the field in a radial pattern around that particular charge. Okay, so that scientists and learners like you guys are able to represent them, and we can see now that you understand what we mean by an electric field. And guys, the last one, very, very important. When we draw these lines to represent our electric field, guys, please make sure that the lines do not cross. Okay, so what I want to do is just to show you, for example, so if I now draw in a, let's get a color over here, if I now draw a positive charge like this, and I start drawing in my field lines, and we know that my field lines all move away from the charge like this, it's radial, and it's all nice like this. I can't do this, guys. I can't now point them and going in all directions, but now they're crossing themselves. Can you see that? That is actually wrong. Okay, but we do see a lot of these problems coming up when people draw them, and you lose marks very easily because of it. You cannot do it. If you're going to draw, please make sure, guys, you draw it nice and neatly, moving away, so it's positive again, moving away from the charge. Okay, you can put them nice and close together if you want, like that, but notice, guys, they are not crossing at any stage, are they? All right. Notice they're not crossing at any stage. So if you want to draw it and you get this like daisy effect around that charge, that's great. Okay, and that, guys, is just some of the basic introductions on illustrating our fields and drawing our electric fields. John, is there anything that's come up on the Twitter or the Facebook?
Not at the moment, but there's a question that I have, Bruce, and that is, using those field lines, we can actually show, can't we, where the field is strong and where it's weak?
Correct. Basically, it's got to do with the density, how close the field lines actually are to each other. So if you've seen the way I've drawn it over here, can you see now where are the field lines the closest together? Well, you should be able to see that right close to the charge itself, you're going to have a greater density. They're much closer together. And as we radiate outwards, you will see that the field lines separate from each other. So if I now had to, let's get another color so we can see it nicely. If I now had to put in a little charge at that point over there and compare it to a charge at that point over there, I think you'll all agree with me that the charge at that position will probably experience a greater force because it's going to be closer where the field lines are more dense. Further away, where that little charge is, it's not going to experience as great a force. Why? Because the electric field is not as dense further away, and therefore the force will be a little bit weaker. John?
Okay, there is a question that's just come up from Empa. Empha, sorry if I've said your name wrong. Is there a definition for an electric field?
Yeah, I basically did show the electric field definition earlier. Let's just go back up here. Okay, there it is. Guys, just to remind you, so I'll put a little star over here so you can get it down. What is an electric field? It's as measured as the force that a positive test charge would experience in that field. And exactly as I've just been telling John now, guys, the closer we are to that particular charge, the greater the force, because the field lines are going to be much closer, and as we move outwards, the force will be less because the field lines are going to be less tightly packed.
Okay, that's a great definition. Please make sure that you learn that definition and that you've got it on the tip of your fingertips and that you can use it as well. I'm sure we're going to see a little later that we can use it in a calculation as well.
Correct.
But we're going to go to a short ad break. Now, we're going to be back after the ad break and we'll get into some more stuff. But please post your questions. We'd love to hear from you. I'm watching the page and I'm watching Twitter. Remember what our account is, www.facebook.com/learnextra, and our Twitter account is @learnextra. Like to chat to you, please be in touch, and we're going to go to a short break now. We'll be back straight after that. Welcome back, grade 11s. This is Learn Extra Live, and we're dealing with physical sciences this afternoon, focusing on electrostatics. And in electrostatics, we've got to know all about electric fields. Now, some of this is revision from grade 10, but it's really important because you know what? You're going to need to know it for grade 12 as well. So I'm not going to say too much more, but join me on Facebook. That's facebook.com/learnextra, as well as at Twitter. That's @learnextra. We'd love to hear from you. There's a calculator, a Casio calculator up for grabs. I'd like to see a question on electric fields that you've got. And the first person that gives me a really good question that we can put out as a challenge question on Facebook page, they're going to get the details for this calculator. Don't want to waste too much more time. Bruce, you've got something for us on the field patterns.
Great, thank you very much, Sean. Yeah, guys, now that we've got a nice concept of what we mean by an electric field, what happens now in terms of the interaction of electric fields if we bring different charges into proximity with each other? In other words, we bring them closer to each other. And that's the heading that I've got here, is placing charges in proximity of each other so that they're nice and close. And let's just see now how these fields are going to interact. So what I'm going to do, guys, is that I'm going to start now with two unlike charges. Okay, I've got a positive charge over here, and I've got a negative charge over here. Plus Q and minus Q. Again, guys, please notice the direction of the electric field lines. Away from the positive charge and towards the negative charge. Very, very important there. Now, guys, what's going to happen now if I now bring these two charges close together? How are the electric field lines going to interact with each other? Well, guys, if you have a look here, and I'm going to take this one as a specific example, can you see now that the positive charge has a line that's moving horizontally to the right-hand side? The negative charge also has a line moving horizontally to the right-hand side as well. So can you see now, whoops, we've just gone back there. Screen's a bit sensitive, there it is. So what's going to happen, guys, can you see now that ultimately, can you see that these lines can sort of join onto each other at that particular point? And when they get close enough to join or to mix with each other, okay, then we create an electric field pattern which is going to be typical for what happens when we have unlike charges. And you guys all know that unlike charges are going to attract. So in other words, what's going to happen, and I'll just scroll down, we can see now that the electric field lines are going to join with each other. We are going to have the lines moving from positive to negative. So there's our positive, and there's our negative charge there. And this is going to be our attraction. Okay, guys? That's going to be attraction. Unlike charges are going to attract. And therefore, we now have an electric field pattern which represents the attraction of those two particular charges together, where the lines have joined up together, the attractive field pattern. Now, what's the opposite of that? Well, that's going to have like charges. Not so. So let's have a quick look at our example of like charges. I've taken two positive charges. I'm just going to draw them in there for you, although it is mentioned at the bottom. But now can you see what's going to happen here? We've got both of them are giving, or have the electric field lines moving away from the charge. So as I bring them together, can you see now we've got sort of a head-on collision of those two field lines, those imaginary lines that I've drawn there. Now if we have a head-on collision, can they now just nicely link up with each other? Absolutely not. They're going to basically come towards each other, Okay? And because they are like charges, they're going to come towards each other and then deflect away from each other. I've got the pattern here for you, like that. There it is. Can you see now they've come towards each other and deflected? So at no stage can these field lines join up with each other like we had when we had unlike charges. It doesn't matter if they're negative or positive. Both of them are going to be like charges. And therefore, this is what is our field pattern for our repulsion. Okay, we are going to have repulsion of the two charges. And therefore, they're going to move away from each other. And this area here, okay, represents an area of zero force. In other words, they're going to be moving away from each other. That's an area of zero force. There's going to be no forces in that point, because what's happening is that this guy's going to move that way, that guy's going to move that way, and they will not be able to come together. And that's the basics of our radial fields. Guys, very important that we are able to understand this. However, there is another type of electric field pattern that I want to show you, and we're going to explain it in a little bit more detail. And I'm just going to change the slide, and we're going to bring it now, and that is electric field pattern between parallel plates. We've spoken very specifically now about two charges. Okay, we've spoken very specifically about radial fields. Okay, now what happens if we have the object? Well, the objects are basically parallel plates. They're charged parallel plates. So I'm going to bring this diagram up, and I'm going to work a little bit on this diagram with you. Now, if I make the top plate positive, okay, and I make the bottom plate negative, like that. Guys, our same basics still apply. Our electric field lines always move from the positive to the negative. We always illustrate it that way. Now, if we've got a parallel plate, then what we've got are lines moving from positive to negative. And I'll just make it a little bit clearer for you by putting in the arrows, showing the direction from positive to negative. However, there's one difference between the electric field generated by a parallel plate compared to an electric field generated by a charged object. Okay, and that is that this electric field is going to be constant at all points in that electric field. In other words, if I put a little charge, let me change the color because I've got too much pink there. If I put a little charge at that point, or a little charge at that point, or a little charge at that point, the charge at all three of these points will experience exactly the same force as a result of the parallel plates. We call this a uniform electric field. Okay, a uniform electric field. And the word uniform simply means that of the force that these charged objects, those little point charges, are going to experience will be the same at any point. Remember, guys, when we had radial fields, okay, I'll quickly draw it again as a reminder, like this. I'll just draw a quick pattern like this. Take a positive charge like that. And what did we say just before we had the break? Is that if we had a charge at a point, whoops, let's get a different color. Let's get that one. A charge over here, close to the main charge, or a little charge at that point. Can you see now that the field is non-uniform? In other words, depending on the proximity or how close that particular point charge is going to affect the force that it's going to experience. And we can see now, remember, where the lines are closer together, we've got the greatest strength of the electric field, and when the lines are further away, we've got a less or decrease in the strength of the electric field. So guys, parallel plates, if we do show parallel plates, we must remember that we have got a uniform field. Okay. The other thing is I've drawn here, you'll notice that at the ends of the plates, I've drawn them as a sort of curved line like that. That's basically all it is to represent that the electric field can extend a little bit outside the actual boundaries of the parallel plates. And when they move slightly outside the boundaries of the parallel plates, then the field actually does not become uniform. So this over here would be the non-uniform area. Okay, that would be the non-uniform area. So if we had to draw a little dotted line to represent the boundary, that area here would be non-uniform, that area here would be non-uniform, because we're outside the boundary of the plates. So whenever we draw these guys, please make sure you just put a little curly lines on the outside to represent just a little extension of the electric field outside the plates, but remember that they are non-uniform. Okay. John, I think that takes us through our electric field lines and our patterns for repulsion and attraction, as well as introducing our parallel plates. I think we can move on to some calculations.
Let's get into some calculations.
Yeah, now we can do some mathematics. We see how does this all apply? Because I'm talking about this concept of force. So guys, force, as we know, is a measurable quantity. Electric field strength is a measurable quantity. How do we now measure it? And let's now go and have a little look over here. If I can get this thing to move. There we go. And there's the heading that we're going to have a look at, electric field strength. Okay. Now, guys, pay attention here. Take down notes where you have to, because this is actually quite important. So as you can see, guys, we've got our electric field like that, and we've got our radiating field lines away from the charge. Okay. Now, the important thing is, this means that the field strength decreases the further away we move from the charge. Remember, guys, it's radial, it's moving outwards, and therefore the further we go, the decrease in the electric field strength, because the charge will experience less force. Okay, so electric field strength, and here's another important little concept and definition to actually understand. Electric field strength is thus measured as the force that a point charge will experience at that position in the electric field. Guys, we spoke about it earlier. There's a reminder for you. Electric field strength. Okay, so let's see now how we can mathematically manipulate this. Thus, if we're talking about the force that a point charge Q will experience at that position in the electric field, there's a very, very simple little mathematical formula which we can draw up. E, which represents my electric field strength, is equal to F, the force, divided by Q, the charge that's placed in that field. So this is now going to be the force, okay, that the charge will experience, and that's going to be the charge that's placed in the field. Okay, and the little diagram above, I have scrolled a little bit too far, so I'm going to go up a little bit more, like that. There we go. Can you see that diagram there, guys? There's that little charge Q that I've placed up in my electric field, and therefore we're going to work out now what is going to be the electric field strength at that point. So there we can say E is equal to F over Q, okay, to measure my electric field strength at that point, if I know the force and the magnitude of that charge. Okay,
Bruce, before you get into another problem, I think it's time to go to a break. Now, guys, I can see there are lots of great questions coming up onto the page. We're going to get a chance to try and answer some of them. I am trying to give you some answers directly onto the page as well. We'll take some of the good ones and we'll do them in the last little while. But let's go to that break now, and we'll see you after the break. Grade 11s, welcome back. Learn Extra Live. Now we're getting into the calculations. I can hear you crying out, calculations, please. Well, Bruce is going to help us out. Here we go with some calculations. We'll see you in a minute.
Right, guys, welcome back. Just to quickly recap, we're now looking at measuring the electric field strength of a charge, a point charge in an electric field. And we measure the electric field strength. E is equal to the force experienced by that charge divided by the magnitude of that point charge in the field. Now, guys, we've defined the electric field strength in terms of a positive test charge. Do we have to actually have a positive? No, we can use a negative charge as well in the field. Okay, it's just that obviously if you've got a positive charge that's generating the field and you put a negative charge in, it'll be a force of attraction towards the charge that's obviously generating the field. But guys, quickly, we want to get onto the calculations. Before we do that, just a quick look at units, very important, we don't forget units. We all know that that force is measured in newtons. We all know that charge is measured in coulombs, and therefore we now have the unit of electric field intensity, which is the Newton per coulomb, newtons per coulomb. N dot C to the minus 1 represents newtons per coulomb. Okay, so guys, let's put this all together and let's now have a look at a worked example. And what I've got here is a question that says, if a minus 6 microcoulomb charge is placed near a positive charge, experiences a force of 0.3 newtons, calculate the electric field strength at that point. So guys, let's have a quick look at what we're trying to do here. And if we can extend this page, there we go. It's just sticking a little bit. I'm just going to draw it quickly over there. So what we've got is a positive charge, right? So I can draw a little field. You don't have to do this, but if you want to, it makes a bit more sense, then you can go for it like that. And then what we've got is we're taking a little charge over here, which is going to be minus Q, which is equal to minus 6 microcoulombs. Okay, so guys, I think now at that point in the field, okay, there, I think you can see now that that is going to now be attracted towards our positive charge. But how do we do the calculation, guys? Well, first of all, let's write down our data of minus 6 microcoulombs. Now guys, remember we spoke about it last week. Although we've got this in microcoulombs, we must convert it into our SI unit of charge, which is the coulomb. And we must now convert the micro. And how do we do that? Well, a lot of you guys will be saying, well, simply multiply it by 10 to the minus 6 of a coulomb. Remember, a microcoulomb is a millionth of a coulomb. So we convert it by simply saying times 10 to the minus 6. That brings us into the right units. The force that we've been given is 0.3 newtons. Now guys, obviously that'll be an attractive force. You have to basically surmise that. And now we have to, all we have to do is do the calculation. If we can extend the page a bit more. Remember, E is equal to F over Q. Okay, simply substitute in. So it'll be F is 0.3 newtons. Q is minus 6 times 10 to the minus 6 of a coulomb, and extend a little bit more, and E works out to be, if you hit your calculator, and I've done that already, comes out to be 50,000 newtons per coulomb. Okay, and there is the magnitude, and we will have a little negative sign. All that little negative sign means that the electric field is causing an attractive force, okay, on that particular charge. A lot of you guys might want to convert this into scientific notation, and if you want to do that, that's fine, that's great. That will work out to be 5 times 10 to the, let's see how many hops we're going to do to get to that. Be 1, 2, 3, 4, and therefore it's going to be 5 times 10 to the 4 newtons per coulomb. Both of those answers will be 100% correct for you. Okay, so guys, if your calculator does come out with the scientific notation, remember it's exactly the same as saying 50,000 newtons per coulomb. Okay, so guys, that's a very simple way of being able to do it. But is this the only way in which we can calculate electric field strength? Guys, the answer is no. We have got another method of doing it, and this is the one I want to spend a little bit of time on with you guys. And we're going to now look at electric field strength now, based on the fact that what you guys did with Coulomb's law last week. Remember guys, okay, and I'm going to make this a plus Q, I'm going to put it in there. There's my test charge at that point, okay? And what we're going to look at now, sorry, I've just got a little bit too far past it, so I'm going to bring it back, okay? That your electric field strength can also be calculated by measuring the effect that a charge has on a 1 Coulomb point charge placed at a certain distance from that charge. Now that sounds like quite a mouthful. What does it all mean? Well, what it means now, if I take a +1 Coulomb point charge, okay, and I place it here, what effect is this guy going to have on this chap over here? In other words, the big charge on the 1 Coulomb test charge. So in other words, guys, we're now going to be looking specifically at the charge that's creating the electric field, rather than what the force was that a charge placed in a field would experience. Now that might sound quite difficult, okay, but follow what I'm doing now and you'll see how this all works out. Well, what we're going to do now is that you'll remember, guys, because we've got two charges, okay, and I'm going to call this guy big Q, like that, because he's the guy responsible for making the electric field in the first place. If you remember from Coulomb's law that we had that force is equal to K, Q1, Q2 over R squared. So if I substitute Q for Q1 and little q for Q2, divided by R squared, and that's the distance from the center of the charge to the test charge. So now we're bringing in the distance. How far away is this particular test charge placed in the field? Okay? Now, with a little bit of mathematics, we're going to play around a little bit here. And what we're going to do now is that we're going to now take this, okay, that force, and we know that E is equal to F over Q. We've already established it. And I'm going to substitute it in there. Okay? Now guys, you're not going to be asked to do this, but for those of you who like your mathematics, you'll probably like to see how I actually develop this equation. Okay, so I now substitute that force for F, and E equals F over little q. There, I've done it. And guys, can you see now with the mathematics that those two are going to cancel out? The little q's are going to cancel out. Which means, guys, is that we are now, we are now looking at another equation to calculate electric field strength, which is based on now the charge that's actually generating that electric field. We need to know what the magnitude of that charge is, and we need to know how far away the test charge is actually placed. Okay, K, we know, is our electrostatic constant. And guys, be careful. We're dealing with R squared. Okay, so when we do the calculation, and I'll show you how to do the calculation, please don't forget we must square the magnitude of the distance between those two little charges. Okay.
Okay, Bruce, thank you so much for introducing that. Now, we've got a few minutes before the end of the show, but we do need to fit in another break. After we come back, we're going to be taking some questions, and we're going to be looking through another worked example. So don't go away. We'll be back straight after this. Welcome back, Mindsetters. It's great to be with you. Now, remember, this is the Grade 11 show. We're dealing with electrostatics and electric fields in particular. I don't want to speak too much longer. There's some great questions that have come through on the Facebook page. It's going to be really difficult to decide who's got the best question. But Bruce has got a really good example lined up. I want to get him going on it, and I'll let you know after this.
Okay, guys, just before the break, I developed the second of the electric field strength equations, which was basically E is equal to K Q over R squared. In other words, now developing electric field strength based on the actual charge that is generating that electric field. And if we place a test charge in that field, how will we work out that electric field strength? Okay, so here's my example. It says calculate the electric field strength that a 5 nanocoulomb charge would exert on a point charge placed 30 centimeters from that charge. Can you see now how the question has been styled, that we have to now target that particular equation to do our calculation? Quick diagram, okay, we've got a 5 and it's a positive, so I'm going to quickly draw the 5 nanocoulomb charge out like that. Okay, so I'm going to draw the field. Okay, and what we've got is that 30 centimeters away, so I'm going to draw it like that, we have got a little test charge which is going to be plus Q. Okay, there it is. And that now represents R, which is now 30 centimeters. And they want us to work out the value of E. This is a 5 nanocoulomb charge. Okay. Well, guys, can you see now we've got everything that we need for our equation? We've got Q, okay? Q is equal to 5 nanocoulombs. We've got R, there it is, which is equal to 30 centimeters. So, and K, obviously we've got that, that's in our data sheet. It's 9 times 10 to the 9 newtons per meter squared per coulomb, and that's given to you. So guys, let's jump into how we do this problem. Let's work out EI, electric field strength. But before we do that, guys, important to note, we must convert to SI units. And guys, let's just talk a little bit about, let's just scroll that down like this. There we go. Okay. I'll tell you what I'm going to do. I've just run out a little bit of space because I've got a second example there. So I'm just going to move it up slightly. I'm going to work in the space over here. Okay. Guys, if we've got 5 nanocoulombs, guys, we've got to convert nanocoulombs to coulombs. Now, when we talk about nanocoulombs, a lot of you guys would have heard of the word nanotechnology. We're down to a very, very small number. In fact, a nanocoulomb is 1 billionth of a coulomb. Now, how do we scientifically express that? Well, to scientifically express it, all we have to do is show it as 5 times 10 to the minus 9 of a coulomb. What that means is 5 times 10 to the minus 9, we have now divided by 1 billion. Okay. Now, if you want to go and put it into your calculator, 5 divided by a billion, you're going to get 0.00000000005 at the end of the day. Now you've got a very funny number with horrible lots of noughts. So we make it quite simple for you guys. All you have to remember is that when we convert from a nanocoulomb into a coulomb, just simply multiply by 10 to the minus 9. The previous question I did, if you guys are watching, had a microcoulomb, a millionth of a coulomb. Simply multiply by 10 to the minus 6. Okay. So that's now getting our charge into the right units. Now we've got this 30 centimeters. Guys, we can't work in centimeters. We have to work in meters. So what we have to do is to convert centimeters to meters. We have to divide by the conversion factor. All we have to ask ourselves is, how many centimeters in a meter? And that's not difficult. 100 centimeters is going to be 1 meter. So therefore, all we have to do is divide by 100. 30 divided by 100 works out to be 0.3 of a meter. Okay. So all we have to do now that we've got this is plug our corrected units into our equation, which I'm going to do over here. So E is going to equal 9 times 10 to the 9, okay, multiplied, in fact, I'll tell you what I'm going to do, I'm just running out a little bit of space. I'm actually going to rub this guy out over here, and we'll make it much easier doing it that way. How's that? Okay, let's bring it back. We're going to have E is going to equal 9 times 10 to the 9, whoops, that's times. That's our value of K. Q is 5 times 10 to the minus 9 divided by, now guys, please don't forget, we are dealing with R squared. So therefore, my distance, which is converted into meters, which is now going to be 0.3 squared, we plug that into the calculator and we get an answer, if I just look at my sheet over here, answer of 500 newtons per coulomb. And there is our correct answer for our electric field strength. So guys, that's how we now do this type of problem. So, quick summary, there are 2 ways in which we can calculate electric field strength. One is due to an actual charge placed in the field and what force that charge experiences, okay? Or we could say, well, if we take a test charge, we place the test charge in the field. Let's go up here to the diagram. If we place the test charge into the field, that test charge is only going to be 1 Coulomb, so that doesn't count. We don't bring it into the equation. Then we've got the actual field that the charge Q actually exerts, or the charge Q actually produces, and the distance that that test charge is placed from that charge Q. And there now are two ways of calculating electric field strength. John, some questions that come in quickly.
There have been some great questions. The one question that came in quite early was about the similarities and differences between gravitational fields and electric fields. I know the equation looks quite similar, but perhaps you just quickly, in 30 seconds, show us the difference.
Right, so if you have a look at the two equations, that's the gravitational field, okay, which is G m1 m2 over r squared. This is the Coulomb's law equation, K q1 q2 over r squared. You will notice that the similarities are that we are dealing with, or direct proportionalities, between either the product of the masses, when we come to gravitational law, or the product of the charges, when we come to Coulomb's law. And both of them, guys, are divided by the square of the distance between the centers, either the center of the masses or the center of the charges. Okay, both of them measure forces of attraction. In this one will be attraction, okay, but we can also, in Coulomb's law, talk about repulsion as well. So you have attraction and repulsion, because remember, guys, that these charges can either be positive or negative. Okay.
Great, thank you, Bruce.
Is that it?
There are a couple of more, but I think we're out of time, and there are a couple of things that we just need to get to. Sina Temba, your question was brilliant, and you've helped other people, so guess what? We're going to give you the Casio calculator, so I'm going to be in touch with you. Coming up straight after this is Meet the Mindsetter. Remember, Mazoe, last year, grade 11, 2000, class of 2011, grade 12, 100% for physical sciences. Watch out for meeting the Mindsetter. We're going to be watching that. And then, guys, remember as well, we're going to be not on the air next week. There's no live show next week, but you can join us on Saturday. There's a live show on Saturday at 10:30 for grade 12s and grade 11s. You're welcome to join us as well. From me, from Bruce.
Great, guys. Yeah, thank you. Thanks for joining me.
Thanks.
It's been a great show.
Thanks so much for being with us, and we'll see you again in the second term. Bye from me.